This is one basic sheet on continuity and differentiability. Box x sine pi x, and we want to check on the left hand derivative at x equal to k, an integer. We want to check on the left hand derivative of fx at x equal to k, which is an integer. Now, by definition, what's f dashed k minus 0? That is the left hand derivative at x equal to k. That's going to be limit fx minus fk by x minus k. X tends to k from the less than k side. Yes or no? Right? But fk would be 0 because this would involve sine k pi, sine integral multiple of pi. That's going to be 0. So this then is simply limit box x sine pi x by x minus k. X tends to k from the less than k side. Right? Now, what is sine n pi minus theta? What is sine n pi minus theta, where n is an integer, even or odd? Realize that when n is odd, this will be a second quadrant scenario, it will be sine theta. When n is even, it will be the fourth quadrant and it will be minus sine theta. So, it's like it depends on the parity of n, depending on whether n is even or n is odd. This should then be minus 1 to power n minus 1 sine theta. Because when n is odd, n minus 1 will be even and this will become 1. So, when n is odd, this will become sine theta. When n is even, this will be odd, n minus 1 will be odd and this will become minus sine theta for n even. Right? So, sine n pi minus theta is minus 1 to power n minus 1 sine theta, right? Or I could also say sine theta, this minus 1 to power n minus 1 can occupy a place here as well. So, that's like minus 1 to power n minus 1 sine n pi minus theta. Right? Isn't it? The reason I did that was, see, this is sine theta, right? I could write this as minus 1 to power k minus 1, minus 1 to power k minus 1 sine k pi minus theta. This is how I could write this. K pi minus theta, theta is, reason I did this was because, I required a sine x minus k kind of a thing. See, now a sine x minus k kind of a thing appears, sine x minus k by x minus k, where x tends to k, it will be of the form sine something by something as something tends to 0. And then, since I have like a pi into k minus x here, so what I do is pi into k minus x, and I plunge a minus to adjust this, and I multiply with a pi throughout to balance this. I hope you realize why we did this. X tends to k from the less than k side. Yes or no? You know why we did all this? Why we carried out this transformation? So that I could bring it of the form sine theta by theta as theta tends to 0. This is k into pi minus x. Pi into k minus x, pi into k minus x. So sine theta by theta as theta tends to 0. Right? So we then left. Now when x tends to k from the less than k side, that means to the immediate left hand neighborhood of x equal to k. Box x is identically equal to k minus 1. Not that it tends to k minus 1, it's identically equal to k minus 1. So box x can be written as k minus 1. The minus 1 and this minus 1 will simply become minus 1 to power k. And then this will be 1 sine theta by theta, and this will simply be 5. That's the left hand derivative at x equal to, that's the left hand derivative at x equal to k. Is that all right? Fx is a function such that f of x plus y is f of x plus f of y, and f of x is sine x gx for all xy belonging to the set of real numbers. Gx is continuous for all xy. We want to be able to find f dash x. We want to be able to find f dash x. Given that g0 is k, we want to find f dash x. This is what we want to do. Right? Again, go from first principles. F dash x is limit f of x plus h minus f of x by h as h tends to 0. Right? Hey, but f of x plus h is going to be f of x plus f of h. So f of x would get cancelled. You simply be left with limit f of h by h as h tends to 0. Right? Hey, but f of h is sine h gh. Is sine h gh. Now, this is product limit of the product of two functions, sine h by h and gh. Sine h by h and gh. Limit of the product will be product of the limits provided both limits exist. In this case, this limit exists and this limit also exists because gx is continuous, right? So then I could write this as limit of this into limit of this. Limit of this is 1. So we are left with limit gh, h tends to 0. Hey, but gx is continuous at x equal to 0. So gh must, limit gh, h tends to 0 must be g0. Why? Because gx is continuous at x equal to 0. So this will be g0, which will be a. Are you alright with this? Now one thing, if a function is given in this form, you could actually arrive at the form of the function. For example, f dash h turns out to be limit fh by h, h tends to 0, right? Now, if you put x equal to y equal to 0 in this, because it's true for all xy, so if you put x equal to y equal to 0, then you get f0 is 2f0, leading to f0 equal to 0, leading to f0 equal to 0. Now, what I get from this connectivity is f dash x is limit f of h minus f of 0, because f0 is 0, divided by h as h tends to 0. What is this supposed to be? Sorry? What is this? Why are you tentative? Be loud. What is this? Huh? Left hand, right hand nahi hai yahan pe. Tell me, what is this? Huh? f dash, this is fh minus f0 by h minus 0. F dash 0. Limit f of something minus f0 by something minus 0 is that something tends to 0 is f dash 0, isn't it? No? So this is f dash 0, which is the derivative of fx at x equal to 0. So this is a constant. That means f dash x is a constant. That means f dash x is a constant. F dash x is a constant. Then fx has to be, when you integrate this is like d dx of f dash x equal to f dash 0. d dx of f dash x equal to f dash 0. Which means d of f dash x is f dash 0 dx. Right? Integrate both sides. Integral d of f dash x will be f dash g of fx. Sorry, this is d of fx. F dash x is d dx of fx. So, okay. Integral d of fx will simply be fx. And the right hand side is f dash 0 comes out into x plus a constant of integration. Right? Hey, but at x equal to 0, f is 0. f0 is 0. So put x equal to 0, left hand side is 0. This is 0. So c must be 0. Right? So because f0 is 0, it leads to c equal to 0. And therefore fx has to be of the form f dash 0 into x, where f dash 0 is a constant, some constant, k prime, let's say. So k prime into x, fx is some constant into x. So every time f is of the form such that f of x plus y is f of x plus f of y, you can quickly conclude that f of x must be some constant times x. F of x must be some constant times x, right? The number of points of discontinuity of this function? 3. 1 of course is x equal to 0 because log is not defined there. And then every time log of this becomes equal to 0, that means whenever mod x becomes 1, that means whenever x becomes plus minus 1, this is rendered undefined. So plus minus 1. So 3 points of discontinuity of this function. So here we have a situation where f of x is sin x and hx is defined as g of fx. We want to be able to find h dashed pi by 2. One thing, hx is g of fx, where fx is sin x, right? But g of sin x is box sin x plus 1, is box sin x plus 1. Hey, do you remember this? Box of x plus an integer would be box x plus an integer. For any real x, box of x plus an integer is going to be box x plus an integer, right? So this is like box of something plus 1. 1 is an integer. So this is going to be box of sin x plus 1, right? Now, h dashed pi by 2 is limit hx minus h pi by 2 by x minus pi by 2 as x tends to pi by 2. Definition. But what's h pi by 2? H pi by 2 is 2 because box 1 plus 1. So h pi by 2 is 2. Yes or no? H pi by 2 is 2. So this is like limit box sin x plus 1 minus 2 by x minus pi by 2 as x tends to pi by 2. Clear? Now, this is like limit box sin x minus 1 by x minus pi by 2 as x tends to pi by 2. Yes or no? Now, we'll look at the region to the immediate right of x equal to pi by 2 and the region to the immediate left of x equal to pi by 2 to examine the left hand and the right hand derivatives of this function at pi by 2. So then, limit x tends to pi by 2 from the less than pi by 2 side is box sin x. Okay. Now, when x is slightly less than pi by 2, sin x lies between 0 and 1. So, box sin x will be identically equal to 0. Box sin x will not tend to 0 but will be identically 0. So, this becomes identically 0. We are left with minus 1 by x minus pi by 2. Now, as x tends to pi by 2 from the less than pi by 2 side, 1 by this tends to, let's say, it becomes larger and larger and larger. So, this tends to like minus infinity. This tends to like minus infinity. Clear? So, first of all, it's not finite. And then limit x tends to pi by 2 from the greater than pi by 2 side. Again, when x is slightly greater than pi by 2, sin x will still lie between 0 and 1 and box sin x will still be identically equal to 0. Not that it tends to 0, it's going to be identically 0. So, 0 is going to be minus 1 by x minus pi by 2. That means, now in this case, I'm sorry, this will be plus infinity because there is a minus sign. This tends to minus infinity because see x is slightly less than pi by 2, so this is negative. So this will tend to minus infinity, so this is going to be plus infinity. X tends to pi by 2 from the greater than pi by 2 side. This you realize will tend to minus infinity. So neither the left hand derivative is finite nor the right hand derivative is finite and they're not equal to each other for sure. So the function does not have a derivative at x equal to pi by 2. The function does not have a derivative at x equal to pi by 2. X cube signum x, and we want to check on its derivative at x equal to 0. Signum x, I repeat, was the following function. For x greater than 0, signum x was plus 1. For x less than 0, signum x was minus 1. For x equal to 0, it was 0. Obviously, it was discontinuous at x equal to 0 and the nature of discontinuity was irremovable, irreparable, irredeemable. Left hand limit is minus 1, right hand limit is plus 1. The value is again a third value. Value at x equal to 0 is again a third number 0. Now, fx is x cube signum x. Let's check on the derivability of this at x equal to 0. F dashed 0 from the greater than 0 side. Greater than 0 side. This is going to be limit fx minus f0 by x minus 0. X tends to 0 from the greater than 0 side. That's the right hand derivative at x equal to 0 by definition. This is going to be limit x cube signum x minus f0 is 0. f0 is 0 divided by x as x tends to 0 from the greater than 0 side. This is like limit x squared signum x, x tends to 0 from the greater than 0 side. When x is slightly greater than 0, slightly greater in the entire neighborhood to the right of x equal to 0, signum x is identically equal to plus 1. So this is identically equal to plus 1 to the right hand neighborhood, so this will become 0, right? And similarly, f dashed 0 minus 0, everything will remain the same. This will be like limit x squared signum x, x tends to 0 from the less than 0 side. When x is slightly less than 0, signum x is identically equal to minus 1. So you can replace this by minus 1. So minus 1 into x square as x tends to 0 will still be 0. So the left hand derivative at x equal to 0 is equal to the right hand derivative at x equal to 0. And the function is differentiable at x equal to 0. The function is differentiable at x equal to 0. Got me? Can I wipe this off? Box of root 2 sin x we want to investigate. But in general, let me talk about box of fx first and then come back to this. In general, let me talk about y equal to box of fx and then investigate this. One thing that you've learnt is when I have box of x, it will be discontinuous every time x is an integer. Every time x is an integer. The quantity inside the box, if it becomes an integer, then those values of x are pertinent values to investigate the function for continuity or otherwise, right? Now, if instead of box x, if I had box of fx, now what are the values of x that must be looked into to investigate this function for continuity or otherwise? Number one, there could be values of x for which the quantity inside the box, that is fx itself, is discontinuous, right? Those are values to be investigated, right? Value or values of x for which fx is discontinuous, then those values of x would constitute points of discontinuity for box of fx for sure, right? Second, for which fx is continuous but fx equal to an integer. I'll have to wait till this stops ringing, otherwise it's going to come in the way of the recording. Why do they have to call me at this time? Hate it. Alright, now these are important values of x. Every time the quantity inside the box becomes an integer, then I have to investigate fx, box of fx, for continuity or otherwise. Now, various possibilities as far as case 2 is concerned. Various possibilities as far as this is concerned. This, of course, we understand what's going to happen. If at x equal to a, fx is itself discontinuous, then you can conclude that box of fx would also be discontinuous. But now, fx is continuous at x equal to some a, but at x equal to a, fx is continuous, but fx assumes an integer value. Fx assumes an integer value. What happens? Let me talk about this slightly greater details. Y equal to fx at x equal to a, some real a, fx is an integer I, fx equal to an integer I, right? This is the case, and fx is also continuous. Fx is an integer and is continuous. Now, one of the things is, at x equal to a, it could be monotonic, either it could be monotonically increasing or it could be monotonically decreasing, right? So, case 1 is when it's monotonic at x equal to a. Monotonic means, let's say, it's like this. It's monotonic at x equal to a, and at x equal to a, it assumes a value equal to I. It assumes a value equal to I, integer value equal to I. Now, if on the same plot, I have to represent box of fx in the neighborhood of x equal to a. See, all that is required is what is transpiring in the neighborhood of x equal to a. That will determine the limit of box of fx as x tends to a, right? When x is slightly greater than a. When x is slightly greater than a. Realize that fx is slightly greater than I. Fx is slightly greater than I to the right of x equal to a. Fx is slightly greater than I. So, box of fx to the right of x equal to a would be identically equal to I, right? Means box of fx to the immediate right of x equal to a as well as x equal to a will be I, right? Will be equal to I to the immediate right of x equal to a. Box of fx would be I. Now, to the left of x equal to a, immediate left of x equal to a, realize that fx is slightly less than I. Fx is slightly less than I. So, box of fx to the immediate left of x equal to a is going to be I minus 1. Yes or no? Is going to be I minus 1. So, box of fx to the immediate left of x equal to a to the exclusion of x equal to a is going to be I minus 1. Is going to be I minus 1. Yes or no? With the discontinuity at x equal to a. To the immediate left of x equal to a, box of fx would be I minus 1 at a, and to the immediate right of x equal to a, box of fx is I. So, do you realize that the left hand limit at x equal to a is I minus 1, the right hand limit at x equal to a is I. So, the function is terribly discontinuous at x equal to a. Nature of discontinuity is irremovable. So, irremovable discontinuity at x equal to a. Irremovable discontinuity at x equal to a. Which means, if a function fx assumes an integral value at x equal to a, and at x equal to a, it's monotonic, then for sure it's discontinuous at x equal to a. For sure it's discontinuous at x equal to a. And whatever I have said of monotonically increasing, you can check for yourself. It's going to be true for fx decreasing. Even if fx was monotonically decreasing, the only difference is I minus 1 and I, they would get swapped. It will still be discontinuous at x equal to a if it was monotonically decreasing. So, whenever the function is monotonic at x equal to a and it assumes an integer value at x equal to a, box of fx is going to be discontinuous at x equal to a. Nature of discontinuity will be irremovable, right? Next, the function is not monotonic at x equal to a. If it's not monotonic at x equal to a, it must have a stationary point at x equal to a. Stationary point means it could either be a local maximum or it could be a local minimum at x equal to a. So these are two more cases that I have to investigate, right? So let's say at x equal to a, we have a local maximum, and the function assumes an integral value at x equal to a I. There is a local maximum very clearly to the immediate right of x equal to a, that is a plus 0. The function is slightly less than I. To the immediate left of x equal to a, again the function is slightly less than I. Yes or no? Which means to the immediate right of x equal to a, it's identically equal to I minus 1. To the immediate left of x equal to a, it's identically equal to I minus 1. But at x equal to a, it's I. Which means box of fx in the proximity of x equal to a will be at x equal to a, it's equal to a value I. To the immediate right of x equal to a, slightly less than I, so box of fx would be I minus 1. To the immediate left of x equal to a, fx again is I minus 1 because fx is slightly less than I, so box of fx would be identically equal to I minus 1. So left hand limit at x equal to a is I minus 1. Right hand limit at x equal to a is I minus 1. The value of the function at x equal to a is I. Is it continuous at x equal to a? No. Nature of discontinuity? Removable discontinuity, because the left hand and the right hand limits are equal. The value of the function at x equal to a is, so it is discontinuous but removable discontinuity. So now the nature of discontinuity has lessened, has mitigated. The extent of discontinuity has lessened from monotonicity to a local maximum. It's discontinuous but to a lesser degree, so to say, loosely speaking, right? Now, so that was the case of a local maximum. So fx, if it assumes an integral value at x equal to a and has a local maximum at x equal to a, it will be discontinuous, but the nature of discontinuity will be removable, right? Now, the third case, which is a local minimum at x equal to a. It has a local minimum and assumes an integer value at x equal to a, right? That's the case, that's case 3. Local minimum at x equal to a. At x equal to a, it assumes an integer value I and has a local minimum at x equal to a. To the immediate right of x equal to a, fx is slightly greater than I. To the immediate left of x equal to a, also it's slightly greater than I, which means box of fx in the immediate right hand neighborhood would be I. Box of fx in the immediate left hand neighborhood of x equal to a will be I. The value of the function at x equal to a will be I, right? and therefore it is continuous at x equal to a. Do you realize that? So box of fx drawn in the proximity of x equal to a is going to be at x equal to a, it assumes a value equal to I. The immediate right hand neighborhood, it's I. Immediate left hand neighborhood, it's I. The function is box of fx is continuous at x equal to a, where it assumes an integer value at x equal to a, and it has a local minimum at x equal to a. So look at the transition. When it was monotonic at x equal to a, it offered discontinuity of a irremovable kind. When it had a local maximum at x equal to a, it was still discontinuous, but of a milder variety. It had removable discontinuity, and then when it eventually boiled down to a local minimum, it was still discontinuous. It lost all its discontinuity. It became a continuous function. So that's the transition from monotonicity to a local minimum via a local maximum. This is what happened, right? This fact you must remember, very useful towards MCQ kind of situations, right? In fact, if you look at number 10, and if fx is not an integer at x equal to a, see, just one last word on this. If fx is not an integer at x equal to a, right? But is continuous at x equal to a, At x equal to a, it assumes a value p, which is not an integer. At x equal to a, let's say fx assumes a value p, which is not an integer. Yes or no? Which means now, if you look at the neighborhood around x equal to a, slightly greater than a and slightly less than a, this will be like slightly greater than p, and this will be slightly less than p, right? This will be slightly greater than p and slightly less than p. In fact, p in general, if it's not an integer, it will lie between two integers. I and I plus 1. If p is not an integer, it will be sandwiched between two integers I and I plus 1. That means slightly greater than p or slightly less than p will also lie between I and I plus 1. Yes or no? Slightly greater than p or slightly less than p will also lie between I and I plus 1. So then, if I take the box of this or the box of this, it will still be I. Because slightly greater than p or slightly less than p will be still sandwiched between I and I plus 1. And the box of all these numbers in the entire neighborhood surrounding x equal to a on both sides will still be, right? Got me? So then what happens? At x equal to a, it's I. To the right of a, it's I. To the left of a, it's I. That means y equal to box of fx at x equal to a, it's in the entire neighborhood around x equal to a, it will be I all the way. X equal to p, box would be I. To the left of p, still be I. To the right of p, will still be I. So the function is continuous at, box of fx will be continuous at x equal to a if fx is not an integer. Assuming that fx itself is continuous at x equal to a, right? Makes sense? Let me just explain in this context. Problem 10. x greater than 0, less than 2 pi. Okay, in this interval, cos x plus sin x is continuous and differentiable everywhere. So not an issue as far as cos x plus sin x is concerned for any x, right? So then those values of x for which cos x plus sin x is an integer would have to be examined. Cos x plus sin x is an integer in the interval 0 to 2 pi. Needs to be examined for x belonging to, okay, at x equal to pi by 2, it's an integer, right? At x equal to 3 pi by 4, it's an integer. Why? Because one will be plus 1 by root 2, the other one would be minus 1 by root 2. So it's an integer. At x equal to pi, again, one would be minus 1, the other one would be 0, right? 5 pi by 4, no, because both would be minus 1 by root 2. The tan quadrant, right? Both would be negative. So this will not be an integer. 3 pi by 2. At x equal to 3 pi by 2, sine would be minus 1, whereas cosine would be 0. So 3 pi by 2. And then the fourth quadrant, where cos could be 1 by root 2 and sine would be minus 1 by root 2. So that means x equal to 2 pi minus pi by 4, that means 7 pi by 4. X equal to 7 pi by 4, which is the fourth quadrant case where cos x is 1 by root 2 and sin x is minus 1 by root 2. Right? So this becomes an integer. So these are the points that have to be investigated. Right? They would all offer discontinuity as long as a local minimum is not encountered at any one of these points. As long as a local minimum is not encountered at any one of these points. Now, what is the least value of this function? Realize that this could be written as root 2 sin x plus pi by 4. Cos x plus sin x could be written as root 2 sin x plus pi by 4. The minimum value of this function is minus root 2, right? Which anyways is not an integer. So if the minimum, right, so the minimum is not an integer. So if at any value of x a minimum is obtained, then that point need not be investigated at all, right? So none of these values will give me cos x plus sin x equal to minus root 2, because these give me values of cos x plus sin x which are integral and not equal to minus root 2. So at none of these values is a local minimum corresponding to fx equal to minus root 2 is obtained. So these are all points of discontinuity of the function. These are all because fx, the quantity inside the box, assumes an integer value, and at none of these values does it assume a local minimum which is an integer. It's not just a local minimum which is also an integer. It assumes an integral value but not equal to minus root 2 at any point. That means that at none of these values does it assume a local minimum. So 1, 2, 3, 4, 5. 5 points of discontinuity. 5 points of discontinuity in the interval 0 to 2 pi to the exclusion of 0 and 2 pi. Are you alright with this? Now, box of root 2 sin x. Hey, one thing, fx is periodic, inheriting its periodicity from sin x. Sin x has periodicity 2 pi, so box of root 2 sin x has periodicity, has a fundamental period 2 pi. So whatever you see of this function from 0 to 2 pi, the same character would be replicated down the line for other values of x. Is that alright? So it's enough to check on this function in the interval 0 to 2 pi, which is a full period of the function, and all possibilities will get exhausted in this interval, right? Now, root 2 sin x (0 pi to pi), where this is root 2, this is minus root 2. Is that okay? Now, n pi by 2 plus pi by 4 kind of a thing. Okay, whenever n is odd, then n pi by 2 would either be this line or it would be this line. Yes or no? Isn't it? This corresponds to n equal to odd. This also corresponds to n equal to odd. N pi by 2 would correspond to these lines. Yes or no? Right? N pi by 2 when n is odd would correspond to these lines. Now n pi by 2 plus pi by 4. So this is like a n pi by 2, one possibility. The other possibility of a n pi by 2 is this, whenever n is odd. So plus pi by 4, this would be n pi by 2 plus pi by 4 kind of a thing when n is odd, or this would be n pi by 2 plus pi by 4 kind of a thing when n is odd, right? So n pi by 2 plus pi by 4, let me imagine this. Very clearly, at x equal to odd multiple of pi by 2 plus pi by 4, this will assume a value either plus 1 by root 2 or minus 1 by root 2. Sin x will assume a value either plus 1 by root 2 or a value minus 1 by root 2. That means root 2 sin x will either be plus 1 or will be minus 1. In this case, it's plus 1. In this case, it's minus 1. Right? So let me look at this case first. Right? Where at x equal to n pi by 2 plus pi by 4, root 2 sin x is plus 1. Clear? Now, when x is slightly greater than, let's say, x not equal to n pi by 2 plus pi by 4, when x is slightly greater than this, realize that this value is slightly less than 1. So box of this will be 0. Box of this will be 0. That means the left hand limit, as x comes closer and closer to n pi by 2 plus pi by 4, box of root 2 sin x will be 0. Because root 2 sin x will lie between 0 and 1. So box of root 2 sin x will be identically 0. That means to the right of this, box of root 2 sin x will be identically equal to, right? To the left of this, to the immediate left of this, root 2 sin x will be slightly greater than 1. Root 2 sin x will be slightly greater than 1. So box of all these values to the left will be identically equal to 1. That means the left hand limit will turn out to be 1. The right hand limit will turn out to be 0. You know what I'm saying? So the function would offer discontinuity of a irremovable kind at x equal to n pi by 2 plus pi by 4 every time n is an odd number, right? So this is one possibility. As far as this is concerned, this is also n pi by 2 plus pi by 4. This also is n pi by 2 plus pi by 4. And here it assumes a value minus 1. And to the right of this, it's slightly greater than minus 1. To the left of this, it's slightly less than minus 1. That means when you come from the right hand side, since it's slightly greater than minus 1, the box of these numbers will be minus 1. When you come closer to this value, these ordinates will be slightly less than minus 1. So box of these will be minus 2. Minus 2. Slightly less than minus 1 means the box will be minus 2. So the left hand limit at this would be minus 2. The right hand limit would be minus 1 and therefore it would be a point of discontinuity at x equal to n pi by 2 plus pi by 4 every time n is an odd number. Clear? Now when n is even, what happens when n is even? Makes sense to all of you, right? N pi by 2 plus pi by 4 when n is even. When n is even, it will be an integral multiple of pi eventually. It will be an integral multiple of pi plus pi by 4. Integral multiple of pi means, let's say, these are the values, 0, pi, 2 pi. These are integral multiples of pi, right? 0 and pi, for example, are n times pi by 2 when n is even. 0 and pi by 2, for example, are n times pi by 2 when n is even. And then plus pi by 4. So n pi by 2 plus pi by 4 would be this ordinate. This point would correspond to n pi by 2 plus pi by 4 when n is no. Now again at x equal to pi by 4, it will assume a value 1 by root 2. So this will be 1. So this will be 1. And when x is slightly greater than this pi by 4, then this will be slightly greater than 1. Box of these ordinates will be 1. Box of these ordinates would be 1. That means to the immediate right of this, box of these ordinates would be 1. That means the right hand limit would be 1. And to the immediate left of this, the ordinates are slightly less than 1. So the box of these ordinates would be 0. So the left hand limit at this point would be 0. The right hand limit would be 1 and the function therefore would be rendered discontinuous at x equal to n pi by 2 plus pi by 4 even when n is an even number. So even or odd, n pi by 2 plus pi by 4 for fx equal to root 2 box of root 2 sin x would always offer discontinuity, right? At x equal to n pi, for example. Now this is n pi, right? To the left of this, it's greater than 0. To the right of this, it is less than 0. So slightly less than 0. So the box of these numbers would be minus 1, whereas the box of these numbers would be 0. So the left hand limit at n pi would be 0, whereas the right hand limit would be minus 1. So the function at x equal to n pi will be discontinuous, and therefore not differentiable, yes or no, right? Got me? So that takes care of all the options. Fx is periodic, inherits periodicity from sin x. Maximum value of fx is 1 in the interval minus 2 pi to 2 pi. Right. Fx is discontinuous at x equal to n pi by 2 plus pi by 4. Fx is differentiable at x equal to n pi where n is an infinite. Right. f dash 0, derivative of this function at x equal to 0. Mod x square is the same as x squared, right? Lambda plus gamma times x squared is differentiable at x equal to 0. But mod x is not differentiable at x equal to 0. And sum of a differentiable and a non-differentiable function will be a non-differentiable function, which means the very existence of mu times mod x prominently will cause lack of differentiability, right? So you don't want this expression, this term to exist in the expression. So you want mu to be 0. You want mu to be 0. So for this function to be differentiable at x equal to 0, mod x, which is not differentiable at x equal to 0, should not prevail in this expression at all. And for that, mu has to be made 0. Mu has to be made. Then you will simply be left with lambda plus gamma x squared, which is a differentiable function at x equal to 0. So f dash 0 would then exist. Right? We have a function from R to R. F of xy is f of x into f of y, right? And it's given that f dash 1 is 2, f4 is 4, f dash 4 is what we want to be able to find out, right? Then go from first principles. F dash 4 is limit f of 4 plus h minus f of 4 by h as h tends to 0. That's f dash 4. Right? Hey, but f of, see, I have to deploy this condition somewhere. F of the product, right? F of 4 plus h, I could actually write as f of 4 into 1 plus h by 4. Now I have f of xy, which is going to be f of x into f of y. Right? So let me write f of 4 plus h as f of 4 into f of 1 plus h by 4, and then from these two terms I can take f of 4 common. Right? Now, it would have really helped the very cause if f1 turned out to be 1, because then this would have been f of 1 plus something minus f of 1 by h by 4 I could write with a 4, such that h by 4 tends to 0. This would have been rendered f dash 1. You know, if f1 turned out to be equal to 1, then I could write this as f of 1. Then this would have become f of 1 plus something minus f of 1 by h by 4. I could write this as h by 4 into 4. As h by 4 tends to 0, that would have been f dash 2. Clear? So f of 1, what I do is put y equal to 1 on both sides in this equation. Put y equal to 1 on both sides of the original equation. So you get f of x is f of x into f of 1, which gives me f of 1 equal to 1, which gives me f of 1 equal to 1. Yes or no? So write this one as f of 1. Write this one as f of 1. And bring a h by 4 here. Balance it with a 4 there. As h tends to 0, obviously h by 4 will also tend to 0. So now we have f of 1 plus something minus f of 1 by something. If something tends to 0, it's going to be f dashed 1. It's going to be f dashed 1. So this is f4 by 4 into f dashed 1 into f dashed 1. No. f4 is known, f dash 1 is 2. So this will become 2. This will become 2. Clear? This is another thing that you could have done here. F of xy is f of x into f of y, right? Differentiate both sides with respect to x, keeping y constant. You know what I'm saying? Differentiate with respect to x as if y is constant, as if y is constant, right? Now, when you differentiate f of xy with respect to x, imagining y to be constant. So first differentiate f of xy with respect to xy. That's going to give me f dashed xy. That's going to give me f dashed xy. And then differentiate xy with respect to x, keeping y constant. That's going to give me y. Differentiate xy with respect to x, keeping y constant. That's going to give me y. Yes or no? The right hand side is imagining y to be constant, so fy would be constant. So it's going to be fy into f dashed x. Yes or no? Now in this, put x equal to 1 and y equal to 4. Put x equal to 1 and y equal to 4 on both sides. So you get y equal to 4 means 4. This will become f dashed 4. This will become f dashed 4 equals fy means f4 into f dashed 1 into f dashed. Right? So this gives me f dash 4 is this into this divided by. Got me? Fair enough. Can I wipe this off? We want to examine box of tan squared x at x equal to 0. X equal to 0. Realize that when x is slightly greater than 0. That means, obviously much less than pi by 4. Slightly greater than 0 but less than pi by 4. Tan squared x will be less than 1 and greater than 0. That means box of tan square x will be identically 0. To the immediate right of x equal to 0, to the immediate right of x equal to 0, box of tan square x would be identically 0, Clear? And x is slightly less than 0. Once again, tan square x will still be less than 1 and greater than 0. Right? That means to the left hand neighborhood of x equal to 0, box of tan square x will still be equal to identically 0. At x equal to 0, box of tan square x is 0. That means at x around x equal to 0, in and around x equal to 0, the behavior of box of tan square x at x equal to 0 is 0. To the immediate right of x equal to 0, box of tan squared x is 0. To the immediate left of x equal to 0, box of tan squared x is 0. Do you see that number 1 at x equal to 0, it's continuous? Not only that, the derivative at x equal to 0 is the tangent at x equal to 0. The left hand tangent, the right hand tangent both coincide with this line. The slope of this tangent is 0. So the derivative of box of tan squared x, left hand or right hand, will be 0, So box of tan squared x is differentiable and continuous at x equal to 0, and its derivative at x equal to 0 is, got me? Oh, we just did 10, right? So 11. One thing, at x equal to 0, fx is 0. You can see that, right? When x is not 0, then fx realize is like x squared 1 plus 1 by x squared plus 1 by 1 plus x squared whole squared plus to infinity, and x is not 0. This is an infinite GP series with common ratio 1 by 1 plus x squared. One by 1 minus r. This will be 1 plus x squared. That means limit fx, x tends to 0. That means when x is in the neighborhood of x equal to 0 but not equal to 0, fx is described as 1 plus x squared. That's the description of fx. In the neighborhood of x equal to 0, right hand or left hand neighborhood, it's described as 1 plus x squared. That means the limit of the function left hand or the right hand limit at x equal to 0 is 1, whereas the value of the function at x equal to 0 is 0. The function therefore is not continuous at x equal to 0. The function is therefore not continuous at x equal to 0. Clear? Now, does it make sense to all of you? Can I wipe this out? All along I have been telling you to avoid using one thing, which is L'Hopital's rule, because I wanted you to get comfortable with limits from first principles. But right now, about time, because this is a pragmatic approach for exams, limits of the kind fx by gx, x tends to a, where fx tends to 0 and gx tends to 0 as x tends to a, or fx tends to plus or minus infinity and gx tends to plus minus infinity as x tends to a. Two situations, both numerator denominator become smaller and smaller in magnitude as x tends to a, or both numerator and denominator become larger and larger in magnitude as x tends to a. Then if fx and gx are differentiable at x equal to a, then limit fx by gx as x tends to a is going to be limit f dashed x by g dashed x as x tends to a. That means you can differentiate the numerator and denominator as x tends to a and arrive at the limit. I mean, limit sin x by x as x tends to 0. Both numerator and denominator are differentiable at x equal to 0, right? And both tend to 0, so it falls within the jurisdiction of this rule, right? So I can differentiate both numerator and denominator cos x by 1 as x tends to 0. This is cos 0, which is 1, right? Limit sin x minus x by x cube as x tends to 0. Again, both numerator denominator are differentiable at x equal to 0 and they tend to 0 as x tends to 0, so I could differentiate numerator and denominator. So this is like cos x minus 1 by 3x squared as x tends to 0. I can differentiate a second time because again as x tends to 0, numerator denominator tend to 0 and they are differentiable at x equal to 0. So this is like minus sin x by 6x as x tends to 0. So that makes it minus 1 by 6. Right? And then there is embedded limit. Sorry, there is another limit, e power x minus 1 minus x by x squared as x tends to 0. Even before I talk of the other kind, let me apply L'Hopital's to this. This rule, by the way, I don't know if I mentioned the name, is called L'Hopital's rule. In school they will call it L hospital. Doctors and nurses around in the form of teachers. E power x minus 1 by 2x as x tends to 0. I can differentiate numerator and denominator to arrive at this, which obviously is half e power x minus 1 by x as x tends to 0 is 1. So this is right. Now, there is another important technique which could be deployed for limits, which is called embedded limit. Limit within a limit, limit within a limit. For example, if I have, let's say, limit e power x minus 1 by x squared as x tends to 0. Let me call it L. Let me call it L. This I can write as limit. Now there is a x square in the denominator. I might want to bring a square of exponential in the numerator. e power something minus 1 whole squared would have helped the cause, right? So I force it in the numerator. So I write this as e power x by 2 minus 1 whole square. So then the middle term is what I brought from outside. So I adjust the middle term, which is like 2 e power x by 2, right? Then this plus 1, the last term, I add it, so I remove that 1. So that along with this will make it minus 2. And then there is a minus x sitting there neatly already. This I could write as limit e power x by 2 minus 1 whole square by x square, x tends to 0, plus 2 times e power x by 2 minus 1 minus x by 2 by x square, x tends to 0. Yes or no? Now, the adjustment to be made here is this, right? Now, again, do you realize that this x square, the numerator is all in terms of x by 2. So I force a x by 2 whole square and adjust it. Why I did that? This is easy. This would be 1/4. And what is the original L? The original L is e power Hong Kong minus 1 minus Hong Kong by Hong Kong square as Hong Kong tends to 0. Right? That's the original limit. And what about this? This is also e power Hong Kong minus 1 minus Hong Kong by Hong Kong square. That's also going to be L. Yes or no? So this will become L by 2. Do you realize that? If that was L, this part will become L by 2. Yes or no? Right? So L, the left hand side, is like a 1 by 4 plus a L by 2. 2 by 4 half, and this will be L. So then I get L by 2 as 1 by 4 or L equal to half. L equal to half. Right? Let me take limit sin x minus x by x cube as x tends to 0. We've already solved this using Laplace, right? Let me give you another approach to the same limit. Call it L. If there was a sine cubed in the numerator, that would have done good to us, right? I can bring in a sine cube because sine x is 3 sine x by 3 minus 4 sine cubed x by 3. Yes or no? Sine theta is 3 sine theta by 3 minus 4 sine cubed theta by 3. Right? Limit. Now this I want to combine with this, right? So minus 4 sine cubed x by 3 divided by x by 3 whole cube with a 27. I hope you realize why I did this, right? And then plus these two terms will collaborate. 3 into sine x by 3 minus x by 3 by x by 3. Again, the numerator has x by 3 as its subject. So I force it to be a x by 3 whole cube and balance it with a 27 here. Hey, this is sine of London minus London by London cube as London tends to 0 is L. So this is also sine of London minus London by London cube as London tends to 0. That's also going to be L. Yes or no? So this is going to become L by 9. This is going to become L by 9. So L then is like minus 4 by 27 plus L by 9, or 8L by 9 is minus 4 by 27. Yes, right? Write down. Let me say limit x ln x tends to 0 from the greater than 0 side. Limit x ln x tends to 0 from the greater than, obviously as x tends to 0 from the less than 0 side, it does not even exist, because to the left of x equal to 0, ln x is not even defined, right? This I can write as limit x into ln 2 into x by 2. No? As x tends to 0 from the greater than 0 side. Let me call all of this n. This is limit x ln 2 plus ln x by 2. X tends to 0 from the greater than 0 side. No? Limit x ln 2 plus x ln x by 2. X tends to 0 from the greater than 0 side. No? This will be 0. Limit x ln 2 as x tends to 0 will be 0. Now this I can write as 2 into x by 2. Right? Hey, same thing. Limit Singapore into log Singapore as Singapore tends to 0 from the greater than 0 side. Limit Singapore into log of Singapore as Singapore tends to 0 will still be L. So this becomes 2L. Yes or no? This will become 2L. So left hand side L is 0 plus 2 times L. So L will be this limit, in fact, I want you to remember limit x ln x tends to 0 from the greater than 0 side. Sometimes down the line in definite integrals, this would be required. So please remember this. The right hand limit of x ln x at x equal to 0 will be 0. Now, few series you must remember. Standard series. For the sake of limit, sometimes they use series expansion. One is e power x, which is 1 plus x square by 2 factorial plus x cube by 3 factorial plus up to infinity. Now, this limit e power x minus 1 minus x by x square as x tends to 0. Okay, e power x minus 1 minus x is what? X square by 2 factorial plus x cube by 3 factorial and so on and so forth. Which is like limit on dividing by x squared 1 by 2 factorial plus x by 3 factorial plus x square by 4 factorial plus other terms that will contain as x tends to 0, which is going to be half, because all of the terms vanish as x tends to 0, right? And then you have the trigonometric series, the sin x and cos x. Sin x is an odd function because of these terms. Realize that if you replace x by minus x, sin minus x will be minus sin x. You can see that, right? The sign of each of these terms will change when you change the sign of, right? That's why sin x is an odd function. So come back to this limit. Sin x minus x by x cubed as x tends to 0. This is like limit. Sin x minus x is minus x cubed by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus up to infinity divided by x cubed as x tends to 0, which is like on dividing by x cubed, minus 1 by 6 plus x square by 5 factorial plus x power 4 by 7 factorial plus up to infinity. As x tends to 0, this will certainly be minus 1 by 6. Right? Similarly, you have like the series for cos x, which is 1 minus x square by 2 factorial plus x power 4 by 4 factorial up to infinity. Even powers of x would cause it to be an even function of x. You have the logarithmic function ln 1 plus x. For x greater than minus 1 less than or equal to 1. Important series log 1 plus x. For x greater than minus 1 less than or equal to 1, it converges to this value log of 1 plus x. Very clearly, you know this limit ln 1 plus x by x as x tends to 0. ln 1 plus x by x is like 1 minus x by 2 plus x square by 3 minus x cubed by 4 as x tends to 0 very clearly is 1. Very clearly is 1. Right? And obviously, you know, the fact that ln 1 plus x by x as x tends to 0 is 1 would cause ln 1 plus x to power 1 by x, right? This 1 by x can come to the power here as x tends to 0 equal to 1. This is what it means. But if the ln tends to 1, that means this must tend to e. 1 plus x to power 1 by x must tend to e. This is what it means. Because the ln of it tends to 1. That means limit 1 plus x to the power 1 by x as x tends to 0 must be yet another technique which is kind of very versatile in its character. Can I wipe this off? You know, coming back to this limit e power x minus 1 minus x by x squared as x tends to 0. We solved it using L'Hopital, we solved it using series expansion, we solved it with the help of embedded limit. Now, let me tell you yet another way of handling this. Let me assume that the limit actually exists. That means the left hand limit is the same as right hand limit, right? We'll keep assuming that until such time that we arrive at something bizarre, something that contradicts, and then we'll dump the original proposition. Limit e power x minus 1 minus x by x squared. Realize that, let me look at the right hand limit of this. That must be the same as the left hand limit of this. That must be the same as the left hand limit of this. less than 0 side, right? Now in this I can replace x by minus x, and then I can say x tends to 0 from the greater than 0. Yes or no? In this expression I can replace the x by minus x, and then x will tend to 0 from the greater than 0 side. Yes or no? If x tends to 0 from the less than 0 side, minus x tends to 0 from the greater than 0. No? You know what I'm saying? This is the same as minus 1 plus x by x squared. X tends to 0 from the greater than 0 side, replacing x by minus x. No? Clear? Now, if this is equal to this, then each would be half their sum. If this limit is equal to this limit, then each would be half their sum. Each would be half of limit this plus this. This plus this means x and x would get cancelled. You are left with like e power x minus 1 plus e power minus x minus 1 by x squared as x tends to 0. No? This I can write as half of limit. Writing this as 1 by e power x. So we have like a e power 2x minus 2 e power x plus 1 by x squared e power x. X tends to 0 from the greater than 0 side. This is e power x minus 1 whole square. E power x minus 1 whole square. Yes or no? What is this supposed to be? 1? E power x minus 1 by x whole square is 1. This is 1. So this will become half. It's another way of looking. Right? Now, let's say there is a certain function y equal to fx. There is a certain function y equal to fx. And in the neighborhood of x equal to a, I have two other functions. Let's say y equal to gx and y equal to hx. Gx is called the upper bound function because higher than fx in the neighborhood of x equal to a, it's higher than fx. So it's called the upper bound function. This hx, which is below fx, is called the lower bound function. And if we find that limit gx, so we have the following association. Fx is in the neighborhood of x equal to a. In the neighborhood of x equal to a, fx is less than or equal to gx, but is greater than or equal to. In the neighborhood of x equal to a, we have fx less than or equal to gx, greater than or equal to hx. And if limit gx x tends to a is equal to limit lower bound function hx x tends to a, each equal to L, then it would imply limit fx x tends to a also equal to x. What I mean is, if I have a function y equal to fx and there is an upper bound function gx which is not lower than fx for any x in the neighborhood of x equal to a, and there is a lower bound function which is not above fx for any x in the neighborhood of x equal to a, and if the limit of the upper bound function as x tends to a is equal to the limit of the lower bound function as x tends to a, then the limit of fx as x tends to a will also be the right. That means when fx is squeezed between an upper bound function and the lower bound function, an upper bound function and a lower bound function in the neighborhood of x equal to a, and if the upper bound and the lower bound functions tend to the same limit L as x tends to a, then the sandwiched function, the squeezed function fx will tend to the same limit as the upper bound and the lower bound function at x equal to a. This is called sandwich theorem or squeeze play theorem. Sandwich theorem or squeeze play theorem. This is what this theorem is called. Right? This is another tool used for evaluating limits. For example, if I have to evaluate limit mod x sine 1 by x as x tends to 0. Realize that mod sine 1 by x will always be less than or equal to 1, greater than or equal to minus 1. Right? Therefore, multiplying by mod x throughout, so mod x sine 1 by x will always be less than or equal to mod x, but would be greater than or equal to minus mod x. Right? That means this function, mod x sine 1 by x, is sandwiched between a lower bound function minus mod x and an upper bound function plus mod x. Right? And the limit of the upper bound function as x tends to 0 is 0. The limit of the lower bound function as x tends to 0 is 0. So the limit of this as x tends to 0 must be 0. So the limit of this must be 0. That's sandwich theorem. And if the limit of the modulus is 0, then the limit of the function must be 0 as well. Limit x sine 1 by x as x tends to 0 will also be 0. That's sandwich theorem. Right? Similarly, you could say limit x squared sine 1 by x as x tends to 0 will also be 0. Why? Because x squared sine 1 by x will always be less than or equal to x squared, would be greater than or equal to minus x squared. Limit of this as x tends to 0 will be 0. Limit of this as x tends to 0 will be 0. So the limit of this as x tends to 0 will be 0. That's sandwich theorem. That's got me? Say I have limit as n tends to infinity. Box of x plus box of 2 square x plus box of 3 square x plus box of n square x as n tends to infinity. Hey, one thing, if you recall from the properties of box functions, box of y is always less than or equal to y, but is greater than y minus 1. Remember this? Box of y will always be less than or equal to y, but greater than y minus 1, right? So then, box of 1 square x will be less than or equal to 1 square x will be greater than 1 square x minus 1. Box of 2 square x will be less than or equal to 2 square x will be greater than 2 square x minus 1. Going this way, box of n square x will be less than or equal to n squared x will be greater than n squared x minus 1. Yes or no? From this property, replacing by y by 1 squared x, 2 squared x, n squared x, add all of this. Add all of this. If you add all of this, call it the sum. This s, which is the numerator. The numerator is s. S will be less than or equal to x into 1 squared plus 2 squared plus n squared will be greater than x into 1 squared plus 2 squared plus n squared minus n 1 1 1 1 n times, right? S by n cube. S by n cube. Divide by n cube. Right? So I have s by n less than or equal to x into 1 squared plus 2 squared plus n squared is going to be n into 2n plus 1, n into n plus 1 into 2n plus 1 by 6. Right? Sum of the squares of the first 10 natural numbers. Greater than, same thing, minus 1 by n squared, n by n cubed, and this by n cubed, written separately. Clear? So s by n less than or equal to x by 6 into this n cube. 1 I combine with this, so it will become n squared. And then 1 plus 1 by n, 2 plus 2 by 2 plus 1 by n. There are 3 n's, 1 gets cancelled. 1 with this would be 1 plus 1 by n and 2 plus 1 by n with the third term. The n cube spread over n, n plus 1 and 2n plus 1 and divided. Right? And this will be greater than, same thing, x by 6, 1 plus 1 by n, 2 plus 1 by n, minus 1 by n squared. Right? Now what are we seeking? We are seeking limit s by n as n tends to infinity. This is limit s by n as n tends to infinity. Right? Hey, as n tends to infinity, what does this tend to? 0, 0. So x by 3. This tends to x by 3. The upper bound function tends to x by 3. As n tends to infinity, this tends to 0. Right? And this again tends to x by 3. So the lower bound function also tends to x by 3. The upper bound function tends to x by 3. So s by n as n tends to infinity must also tend to x by 3. So limit s by n tends to infinity will be x by 3. That's sandwich theorem. I'm sorry, n cube. This is n cube. I'm sorry, this is s by n cubed all the way. I'm so sorry. S by n cubed. Sorry. S by n cubed all the way. Clear? So this is yet another tool very commonly deployed for evaluating limits. Okay, come back to the sheet. We want to check this function for differentiability at x equal to 1 and 2. Now, very clearly, isolate x equal to 0 from this interval. When you isolate x equal to 0, this will be 0. Fractional part of 0 will be 0. So the function fx is 0 at x equal to 0, right? When x is greater than 0 but less than 1, what is box x? Box x will be 0. So this will become 0 and fractional part of x will become x. When x is greater than 0 or less than 1, fractional part of x is y. When x is greater than or equal to 1 but less than 2, box x will be 1. Signum of a positive number would be 1. So this would be, okay, x greater than 0, less than 1, x, right, which is this. Greater than 1, greater than or equal to 1, less than 2, box x would be 1. Signum of this would be 1 and this would be like a x squared and this would be x minus 1. This would be x minus 1. See, because fractional part of x is x minus box x. So when x belongs to 1 to 2, box x is 1. So this will become x minus 1. Right? So the first line of description leading to 3 simpler lines of description. Now the next line of description. See, sin x in this interval has no point where it changes behavior. But mod x minus 3 changes behavior at x equal to 3. So break this interval from 2 to 3 and 3 to 4. That's going to be sin x. When x is less than 3, mod x minus 3 would be 3 minus x. Right? When x is greater than or equal to 3 but less than 4, this is going to be sin x plus. When x is greater than or equal to 3, mod x minus 3 will be x minus 3. Yes or no? Right? Now one thing for simplicity, see, when x is 0, it's 0. When x lies between 0 and 1, it's 0. I could have included 0 here because then at x equal to 0, it would still be 0. So just to simplify matters even further, include 0 in the second line of description to have more efficient number of lines of description, right? So then, what is limit fx? X tends to 1 from the less than 1 side. When x tends to 1 from the less than 1 side, the fx is described as x. So this is 1, right? Limit fx x tends to 1 from the greater than 1 side. When x is slightly greater than 1, the description of fx is x square plus x minus 1. So that's 1, right? The value of the function at x equal to 1, at x equal to 1, 1 plus 1 minus 1, that's 1. So the function is continuous at x equal to 1, right? f1 is 1. So function is continuous at x equal to 1, yes or no? Let's look at differentiability of the function at x equal to 1. Let's look at the differentiability of the function at x equal to 1. F dashed 1. F dashed 1 minus 0. Left hand derivative at x equal to 1 is going to be what? Limit fx minus f1 divided by x minus 1 is x tends to 1 from the less than 1 side. That's left hand derivative at x equal to 1. But when x is slightly less than 1, the description of fx is x. f1 is 1 by x minus 1. X tends to 1 from the less than 1 side. Let me look at the right hand derivative at x equal to 1. Limit fx minus f1 by x minus 1, x tends to 1 from the greater than 1 side, right? But when x is slightly greater than 1, the description of fx is x square plus x minus 1. Minus f1 is 1 divided by x minus 1, x tends to 1 from the greater than 1 side. This I can write as limit x minus 1 into x plus 2. The numerator could be factored by x minus 1 as x tends to 1 from the greater than 1 side. Yes or no? Which evidently is 3. So left hand derivative is not equal to the right hand derivative at x equal to 1. So the function is not differentiable at x equal to 1. The function is not differentiable at x equal to 1. Clear? No? Now, one of the things that you could have done, I deliberately chose to do this using first principles, but you could have done the following as well. Once you establish that it's continuous at x equal to 1, what you could have done is f dashed x would have been 1 to the left of 1, but f dashed x would have been 2x plus 1 to the right of x equal to 1. So the left hand derivative would have been 1, the right hand derivative at x equal to 1, 2x plus 1 at x equal to 1 would be 3. You know what I'm saying? But that you can do only subject to having verified the continuity of the function at this transition point. Then you can differentiate it. But if it's not continuous at x equal to 1, then don't differentiate and plug x equal to 1, 2, etc. It's going to be illegal, right? And similarly for x equal to 2. So I've done x equal to 1 for you. You can in a similar manner check for x equal to 2 independently. We want to check this function for continuity or differentiability. Again, the rule of the game is to expand this description into simpler lines of description devoid of the box, the fraction and the signum. That's what you want to do. Now let's say the first line, let's break it up into elementary and more conceivable lines of description. How one does that is, in the interval 0 to 1, this is the first, right? You will have to break it up into sub-intervals. On what grounds? The ground of breaking it up into sub-intervals is, see, this is x equal to 0. This is x equal to 1, which includes 0 but excludes 1 for the first line of description, right? Now, the nodes which would mark transition would be points between 0 and 1, where this function and this function change character. This quantity inside the box changes character every time it becomes an integer. Do you realize that at x equal to half it becomes an integer? So x equal to half is a point between 0 and 1 where this changes behavior. Where this changes behavior. Yes or no? You know what I'm saying? So plug in a x equal to half on the real number line between 0 and 1 first, right? Now x plus 1 by 3, fractional part of something will change behavior every time the quantity inside is an integer, right? This will become an integer at x equal to 2 by 3. This will become an integer at x equal to 2 by 3, yes or no? Right? So x equal to 2 by 3 marks the point where this changes behavior. That's the only point between 0 and 1 where this becomes an integer, that is x equal to 2 by 3. Yes or no? So put x equal to 2 by 3 here. Now, so the intervals would be 0 to half, half to 2/3 and 2/3 to 1. That's the rule. Once you have spread out these points, these nodes where the constituent functions of the line will change behavior, then the intervals will be like 0 to half, half to 2/3, 2/3 to 1 and so on. When x is greater than or equal to 0 but less than half, when x is greater than or equal to 0 but less than half, sin pi x will lie between 0 and pi by 2. Sin pi x will lie between 0 and 1. Box of sin pi x will be, right? Then does not matter what this is. This obviously lies between 1/3 to 5 by 6. When x changes from 0 to half, the quantity inside will lie between 1/3 to 5 by 6, right? So if the quantity inside is a fraction, then the fractional part of this will be x plus 1/3 only. So this will be x plus 1/3 in this proposed interval 0 to half, and this will be 0. So x plus 1/3 into 0, that's going to be 0 for the first line, 0 to half, which includes 0 but excludes. So fx is 0 for this, right? And then half to or 2/3, greater than or equal to half but less than 2/3. Okay, so then this will lie between 5 by 6 and but less than 1. When x is greater than or equal to half but less than 2/3, the quantity inside the fraction will lie between 5 by 6 and 1, not including 1. So then, since this still lies between 0 and 1, the fractional part will be the part itself, x plus 1/3, right? And this lies between pi by 2 to 2 pi by 3, right? This lies between pi by 2 to 2 pi by 3. One of the things is, I should have actually isolated x equal to half here, because at x equal to half, this will become 1 and this will be 5 by 6. This will be 5 by 6 at x equal to half. At x equal to half, isolating 5 by 6, and then looking at x greater than half less than 2 by 3. X greater than half less than 2 by 3 means this will simply be x plus 1/3 like I told you, because this will still be a number between 0 and 1. So this is going to be x plus 1/3, and pi x, this quantity will change from pi by 2 to 2 pi by 3, not including pi by 2. So sign of this will still lie between 0 and 1 because it's a case of second quadrant. So box of this will be 0 into 0. So that's equal to 0. That's the reason, I chose to exclude x equal to half, because at x equal to half, this would have been reduced to 0, which is not the case, because at x equal to half, it has a separate value, 5 by 6, right? And then 2/3 to 1, 2/3 to 1, x greater than or equal to 2/3 but less than 1. Now when x is greater than 2/3, this will be, the quantity inside would be greater than 1, right? But it will be less than 4/3. It will be less than 4/3. That means this will lie between 1 and 2. This will lie between 1 and 2. Fractional part of a number between 1 and 2 would be number minus 1. Fractional part, right? Fractional part of x is x minus box x. So if x lies between 1 and 2, box x will be 1. So fractional part of x will be x minus 1. Yes or no? Giri? Not me. So then, when x is greater than or equal to 2/3 but less than 1, this will be between 1 greater than or equal to 1 but less than 4 by 3. So okay, I shouldn't have included. I'm so sorry. X equal to 2/3 I can include in this line of description. You're right. X equal to 2/3, obviously it becomes an integer. Fractional part will be 0. I want to include in this line of description because this is 0. Yes, you're right. X greater than 2/3 but less than 1. This would be like between 1 and 4 by 3. So this would be this minus 1. This minus 1 is x minus 2 by 3. And this will still be 0. This will still be 0. So it could have been included in this line of description as well because this was 0. So, but yes, you're right. I could have included, not knowing what would happen down the line, I should have included 2/3 there. But then between 2/3 and 1, this will lie between 2 pi by 3 and pi. So second quadrant, it will lie between 0 and 1. Box will be 0. Right? At x equal to 1, this will become like a 4 by, 1 is not included in this at all. So 1 goes to the next line, 1 goes to the next line. So I have been able to describe this fx in these natural intervals, right? The first line. Now come to the second line of description. Let's break it up into simpler subparts, clear? Now when x is greater than or equal to 1, less than or equal to 2, 2x will be greater than or equal to 2, less than or equal to 4. 2x will be greater than or equal to 2 but less than or equal to 4. Now as far as this function is concerned, again, it's important for me to mark these subintervals based on where this changes behavior, right? So 1 to 2, 1 included and 2 also included. This changes behavior every time 2x is an integer. So what are the integer values that 2x assumes? It assumes an integer value between 2 and 4. The integer values of 2x are 2, 3 and 4. The integer values of 2x in this interval would be 2, 3 and 4. So 2x will change behavior at 2, will change behavior at 3, will change behavior, 2x will change behavior at 1, and then when 2x is 3 means when x is 3 by 2, and then at x equal to 2. These are the points where 2x is an integer. So 2x changes behavior at 1 and it changes behavior at 3 by 2. Because at 1, 3 by 2 and 2, 2x is an integer, so box of 2x would have to be broken down into parts accordingly. Now x minus 4 by 3, signum of this. This will change behavior at x equal to 4 by 3. Because when x is slightly less than 4 by 3 or lesser by any amount, as long as x is less than 4 by 3, this will be a negative number, signum would be minus 1. When x is equal to 4 by 3, it's going to be 0. When x is greater than 4 by 3, it will be plus 1. So this changes behavior at x equal to 4 by 3. So my intervals of description would be this, this and this. Right? So then, for x greater than or equal to 1 but less than 4 by 3. For x greater than or equal to 1 but less than 4 by 3, 2x would lie between 2 and 8 by 3. 2x will lie between, see in this interval 1 to 4 by 3, 2x will lie between 2 and 8 by 3. So box of 2x will be 2. Box of 2x will be 2. So 2x will be 2. And since x is less than 4 by 3, x minus 4 by 3 is negative, signum of this would be a minus 1, minus 1. Right? At x equal to 4 by 3, signum will be 0, so this becomes 0. This becomes 0. Now, when x is greater than 4 by 3 but less than 3 by 2, when x is greater than 4 by 3 but less than 3 by 2, signum of this would be plus 1, right? And then 2x will lie between 8 by 3 and 3. That means box of 2x will be 2. Box of 2x will be 2. Yes or no? 2x will lie between 8 by 3 and 3. So box of 2x will be 2 for all points here. For x greater than or equal to 3 by 2 but less than 2. That's the next. Greater than or equal to 3 by 2 and less than 2. 2x will be greater than or equal to 3 but less than 4. So box of 2x will be 3. And signum would be 1 because anyways it's greater than 4 by 3, signum would be 1. And then last bit, at x equal to 2, at x equal to 2, it will be 4, it will simply be 4. At x equal to 2, the value would be 4. At x equal to 2, the function assumes a value equal to 4. Now when you have such simpler lines of description, at every transition point, at every node, you can check for continuity and differentiability in a manner that we've already discussed. Clear? If fx is continuous at x equal to 0, we want to find f0. We want to find f0. If fx is continuous at x equal to 0, then f0 will be limit fx as x tends to 0. If fx is continuous at x equal to 0, then f0 must be limit fx as x tends to 0. That's the definition of continuity at x equal to 0. So then this is like limit cos c minus cos d, 2 sine d minus c by 2 sine c plus d by 2 by, there is a x squared already here, and then I might want to bring this in the denominator, this in the denominator, so x squared minus x minus sine x by 2 x plus sine x by 2 into x squared minus sine squared x by 4 as x tends to 0. I hope all of you understand what I did here. Why this manipulation? Sanjana? Naina? Sin theta by theta, so I brought this theta from outside. Sin theta by theta, so I brought this theta from outside. And then I balanced it here, x squared minus sine squared x by 4. This x square was already sitting there. So this would be 1. And then realize that x squared minus sine squared x by x squared, this will be 1, 1, etc. We have like 2 into x squared minus sine squared x by x squared as x tends to 0. That's limit half 1 minus sine squared x by x squared as x tends to 0. As x tends to 0, sine squared x by x squared would tend to 1. So this will tend to 0. So this limit is, so f0 must be got me? We want to check this function for continuity or differentiability. Continuity and differentiability in the interval minus 2 to 2. Right? Now, there are two kinds of function here. Mod x plus half, which would change behavior at x equal to minus half. To the left of x equal to minus half, it will be minus of x plus half. To the right of x equal to minus half, it will be x plus half. Mod x plus half is x plus half when x is greater than or equal to minus half, is minus of x plus half when x is less than minus. X equal to the left of x equal to minus half, it's this. To the right of x equal to minus half. And box x changes behavior at minus 2, minus 1, 0, 1, 2. Right? So this gives us the blueprint for spreading out the interval. Minus 2, 2, minus 1, 0. This is minus half, 1. These are the points that will determine the interval of description of the function. So we'll take like -2 to -1, and then -1 to -half, and then -half to 0, and then 0 to 1, and 1 to right. When x lies in this interval, what is box x? -2. But mod of box x will be simply 2. Now, in this interval, x is obviously less than -half. So mod of x plus half will be minus of x plus half, right? Right? Then -1 to -half, -1 to -half, right? In this interval, what is box x? -1, but mod of box x will be 1. And x is still less than -half. So mod of x plus half would be minus of x plus half. Right? And then -half to 0. Now x is greater than -half. So mod x plus half will be simply x plus half. And again, since x is less than 0 and is still greater than -1, box x will be -1. So mod of box x will be 1. Right? And then x greater than or equal to 0 but less than 1. In this interval, x is anyways greater than -half. So mod x plus half will be x plus half. And box x will be 0. Right? And then 1 to 2. In this interval, box x would be 1. So 1 and to x plus half. That's this interval. And then x equal to 2. Box x will be 2. 2 into 5 by 2. At x equal to 2, it's 5. Got me? Now, so I have the function described very simply. And you can find at x equal to -1, at x equal to -half, at x equal to 0, at x equal to 1, the continuity, check on the continuity as well as differentiability of the function from first principle. Clear? Did I tell you in the past a property of continuous functions? If a continuous function changes sign in an interval, it must have a root in that interval. So then, look at this interval. At the end points of the interval, this is a continuous function in the interval 0 to pi by 4, right? Look at f0. That's -2. Look at f pi by 4. 2 plus 5 pi by 4 minus 2, which is 5 pi by 4. So this function fx, which is continuous in the interval 0 to pi by 4, has changed sign in that interval, and it must therefore have a root in that interval, at least one root in that. Right? Yes or no? We want to check this function for continuity at x equal to 0. f0 is 0. f0 is 0, right? Limit fx, x tends to 0 from the greater than 0 side. When x is tending to 0 from the greater than 0, that means it's not 0. And when it's not 0, it's described this way, right? Now when x tends to 0 from the greater than 0 side, this will tend to 0. Fractional part of x coming closer and closer to 0 from the greater than 0 side will be 0. What's the graph of fractional part of x? The graph of fractional part of x is like this. As x tends to 0 from the greater than 0 side, realize that the fractional part of x tends to 0, but as x tends to 0 from the less than 0 side, fractional part of x tends to 1, right? So as x tends to 0 from the greater than 0 side, fractional part of x will tend to 0, and this anyways will tend to 0. This will be 0. So the left hand limit at x equal to 0 is, now limit fx, x tends to 0 from the less than 0 side, less than 0 side. Now this will be 0. As x tends to 0 from the less than 0 side, fractional part of x tends to 1, it will be 0. So the right hand limit is 1. So left hand limit and the right hand limits are not equal. The function therefore is not continuous at x equal to 0, is not continuous at x equal to 0. Hey, there are two functions y equal to root 4 minus x squared and y equal to root 1 plus x squared. Now if you look at y equal to root 4 minus x squared, this is like a x squared plus y squared equal to 4. So this is part of the circle. X squared plus y squared equal to 4 is a circle. So y equal to root 4 minus x squared is, see, the entire circle is x squared plus y squared equal to 4 is this circle, right? X squared plus y squared equal to 4 is this circle, this being 2, this being minus 2, right? But we need only those y's that are positive. That means this y equal to root 4 minus x squared is only the upper part of the circle, because y is positive here, but the lower part of the circle, the y's are negative. So this is the circle y equal to root 4 minus x squared, yes or no? This is y equal to root. The lower part is y equal to minus root 4 minus x squared. The lower part of the circle is actually y equal to minus root 4 minus x squared. Then y equal to root 1 plus x squared at x equal to 0, it 1. And as x becomes larger and larger, y becomes larger and larger, right? Y tends to infinity as x tends to infinity. the value that this function has at x is the value that it has at minus x. So then, if it has at x a certain value, then at minus x also it has the same value. So this typically then is the trait of y equal to root 1 plus x squared. Now, let me plot both these in the same xy plane. This is y equal to root 4 minus x squared in the interval minus 2 to 2. At x equal to 0, y equal to root 1 plus x squared. At x equal to 0, it's 1. At x equal to 0, it's 1. This point is 0, 2. Clear? Now, the two graphs intersect at certain values of x. They intersect at those values of x for which 4 minus x squared becomes 1 plus x squared. They intersect, their y's become equal when x's are such. That means when x is root 3 by, when x is root 3 by 2 plus minus root 3 by 2, they intersect at x equal to plus minus root 3 by 2. So they intersect minus root 3 by 2 plus root 3 by 2. Right? Now we are all set to deploy these conditions. Between minus 2 to 0, including minus 2 and including 0, the larger of the two will hold good. Maximum of the two means the larger of the two. That means the graph, whichever is higher in the xy plane, will prevail in an interval, right? So then, from minus 2 to minus root 3 by 2, this graph is higher. So this prevails and this goes away. Right? From minus 2 to minus root 3 by 2, the higher one will prevail, root 1 plus x squared. Then minus root 3 by 2 to 0, this one is higher. So this will stay and this will vanish. Right? At x equal to 0, it's this. Right? Now, from 0 to 2, excluding 0, but including 2. Whichever is lower, minimum of the two means whichever is lower, the lower graph will prevail. Lower, from here to here, the lower part is this. So this will stay put and this will vanish. This is a point on the graph, whereas this is a kink. Right? Then from root 3 by 2 to 2, this is lower. So this will stay and this will go away. Then this is the graph of this fx in the interval. Do you realize that it's discontinuous at x equal to 0? Left hand limit is 2, whereas right hand limit is 1. At x equal to minus root 3 by 2, it's continuous, all right, but it's not differentiable because the left hand derivative, it seems, is this, the right hand derivative is. So it's not differentiable at minus root 3 by 2. Similarly, at plus root 3 by 2, it's not differentiable but continuous. Left hand derivative is this, right hand derivative is. Yes or no? Alright, so we stopped at 18. fx is x minus x squared, gx is maximum of ft, t greater than or equal to 0, less than or equal to x greater than or equal to 0, less than or equal to 1, and is sine pi x. It must be x greater than 1, because x greater than or equal to 0 to 1 is this. So this must be for x greater than 1. There must be a typo here. We want to check on the continuity and differentiability of this fx. Now, let's identify how to discover the form of gx given the form of fx. Fx is a parabola x minus x squared, downward opening parabola with nodes at 0 and 1, right? So the graph of fx is like this. At x equal to half, it becomes 1/4. So this is the graph of fx, right? And we want to check on the graph of gx. We want to check on the graph of gx. For x greater than 1, it simply goes as sine pi x. We need to know how it goes from 0 to 1, gx from 0 to 1. Now, for any x between 0 and 1, gx is defined as maximum of ft, where t runs from 0 to x, which means what? Which means if there is any x from 0 to 1, if there is any x from 0 to 1, right, then this is fx, right? But what is gx? To determine gx, you choose a running variable t. You choose a running variable t from 0 to x. Choose a running variable t that runs from 0 to x. While this t runs from 0 to a certain x, that means from 0 to a certain x, what this t does is, it produces a set of ft's. While this t goes from 0 to a certain x, it produces a set of, these are the ft's, it produces a set of ordinates, right? And if this is fx at x, then gx would be, for a given x, the maximum ft encountered when t runs from 0 to, the maximum ft encountered when g runs from 0 to x. Now, when x lies here, for example, then of all the ft's that are produced, the largest ft is 1/4, but if x were to be to the left of half, then while t goes from 0 to x, it produces a set of ft's, of which the largest ft is, right? So it depends on where x is located. From 0 to half, the behavior is like fx. From half to 1, the behavior would be 1/4, right? So the complete description of gx is, while x goes from 0 to half, that means if t lies anywhere between 0 and half, I populate all the ft's, the largest ft would be fx. Now if, in contrast, x is greater than or equal to half, then this is fx. For any x greater than or equal to half, but less than or equal to 1. This is fx. Now, of all the ft's produced, while t runs from 0 to x, of all the ft's produced, these are the ft. The largest ft encountered in this process is 1. So then gx would be 1/4. Right? And when x greater than 1, it goes like sine pi x anyways. Now this fx is obviously x minus x square, x minus x. So once you have hashed out the simpler form of gx, then it's easy to check on gx for continuity and differentiability at half, at 1, 1, of course. Yes, the left hand limit would be given by this, the right hand limit would be given by sine pi x, and differentiability. If continuity fails at a certain transition point, then you don't go ahead and check for differentiability anyways, right? That's what you do. In fact, you might just want to draw the graph and see what's happening. If you want to draw the graph of gx, from 0 all the way to half, gx simply goes as fx. That is this parabola, right? And then half onwards, all the way to 1, it remains 1/4. It remains 1/4. This is 1/4. This is the graph of gx, right? Evidently, it doesn't, is it differentiable at this point? Actually, it is, because see, the original graph, that is this part, had a tangent like this. This is the left hand tangent. See, the original parabola was like this. At half, the left hand tangent was this. So even if you remove this portion, the left hand tangent will still be this, which gets aligned with the right hand tangent at x equal to half. So it's, in addition to being continuous at half, it's also differentiable, right? And for x equal to 1, it becomes sine phi, which is 0. So that means the right hand limit will be 0, and then for x greater than 1, it's like this sine pi x. At x just about equal to 1, x coming closer and closer to 1 from the greater than 1 side is sine pi, which is 0. And then greater than 1 means greater than pi, then 3 pi by 2, and then 2 pi, and then it goes like this. This is the graph. So obviously at x equal to 1, the left hand limit is 1/4, the right hand limit is 0, not continuous and therefore not differentiable. Clear? Fx is fractional part of x, gx is box x. Number 1, hx is fx into gx. We want to check at x equal to 1 and 2. Fx is like fractional part of x, gx is box x, and you want to check this at x equal to 1. You want to check this for continuity at x equal to 1. Naturally, uh, limit hx, x tends to 1 from the less than 1 side. Obviously, the value of the function at x equal to 1 will be 0 because fractional part of 1 is 0, right? Limit fractional part of x into box x. X tends to 1 from the less than 1 side. Now, fractional part of x, when x is slightly less than 1, box x is identically 0. So it does not matter what fractional part of x, right? So this is going to be 0. Because when x is slightly less than 1, x lies between 0 and 1, box x would be identically 0. So the left hand limit at x equal to 1 is 0 for hx, right? Limit hx, x tends to 1 from the greater than 1 side is limit fractional part of x to box x, x tends to 0, 1 from the greater than 1. When x is slightly greater than 1, box x is identically 1, right? And when x tends to 1 from the greater than 1 side, fractional part of x tends to, see, this is the graph of fractional part of x. This is 1. As x tends to 1 from the greater than 1 side, fractional part of x tends to 0. Yes or no? So this tends to 0 and this is identically equal to 1. So this product will tend to 0. So hx is continuous at x equal to 1. hx is continuous at x equal to 1. h0 is also 0, right? Okay, at x, same hx at x equal to 2. Limit hx, x tends to 2 from the less than 2 side. And the less than 2 side is limit fractional part of x into box x. X tends to 2 from the less than 2 side. When x is slightly less than 2, box x is identically equal to 1. Box x is identically equal to 1. So this is 1. And when x tends to 2 from the less than 2 side, fractional part of x tends to 1. 1. From the less than an integer side, when it comes closer, see, at x, this is 1. As x tends to 2 from the less than 2 side, it comes closer and closer to 1. Fractional part of x. So this is 1. Limit hx, x tends to 2 from the greater than 2 side is, well, when x is slightly greater than 2, box x is identically equal to 2. So this becomes 2 into fractional part of x. X tends to 2 from the greater than 2 side. And when x tends to 2 from the greater than 2 side, fractional part of x tends to 0. So the left hand limit is not equal to the right hand limit. The function suffers from an irreparable discontinuity. Just have I taught Rolle's theorem, Lagrange's theorem to you? No, I have not covered Rolle's theorem, Lagrange's theorem, right? No. Let me quickly give you a brief discussion on that so that my next sheet can contain problems on Rolle's theorem and Lagrange's theorem. Let's say this is a function y equal to fx, continuous and differentiable in the interval a to b, continuous and differentiable in the interval a to b. And fa is fb is 0. fa is fb is 0. The function vanishes at the endpoints of the interval. Function vanishes at the endpoints of the interval. Now, look at the derivative function. At x equal to a, f dash t, as you can see from the graph, is positive because this theta is acute, right? The derivative at x equal to a is positive. Look at the derivative at x equal to b, f dash b. That's less than 0 because this angle is obtuse, which means if I look at the function y equal to f dash x, then in the interval a to b, f dash x changes sign, f dash x changes from positive to negative, and if f dash x is a continuous function, and it changes sign in the interval a to b, it must vanish in that interval at least once. That means f dash x must become 0 at least once in the interval a to b. That's a property of continuous functions. Yep. Which means there must be a certain point x equal to c for which f dash c becomes 0. F dash c becomes 0 means physically there must be a certain point a on the graph of the function. There must exist at least one point a on the graph of the function which is parallel to the line joining the initial and the final points. There must be at least one point a on the graph of the function such that if you draw a tangent at x equal to c that corresponds to the point a, then that tangent must be parallel to PQ. Then that tangent must be parallel to PQ, the line joining P and Q. That's Rolle's theorem. Now, this was the original version of Mr. Rolle, right? But what's the physicality here? The physicality is this is a curve. This is the line joining P and Q. The tangent at A is parallel to the line joining P and Q, right? One of the things is this physicality will remain undisturbed by the choice of coordinate axis, whether this is the x-axis and this is the y-axis, or the axis is moved up or down, shifted laterally. The fact that there is a point A for which the tangent becomes parallel to the line joining P and Q, that's the physicality involved in this description, right? That physical fact is frame independent, right? That's not going to get disturbed. You know what I'm saying? So which means now, if this was the curve where FA and FB were not 0. This was a curve where FA and FB were not 0. This is FA, this is FB, but they were simply equal. FA was to be equal to FB. FA was to be equal to FB. Then what is guaranteed is a point such that the tangent at that point will be parallel to PQ. That's a physicality. The physicality of Rolle's theorem was this: existence of a point A such that the tangent at A is parallel to the line joining P and Q. That means once again, there exists a point C belonging to A to B. There exists a point C belonging to A to B such that f dash C once again is 0. You know what I'm saying? Thank you. Now, realize that essentially I've been able to produce this by moving the frame downwards, move the xy frame downwards. The physicality of this being parallel to this is the same, will remain the same, right? Now, say this was the curve. In this case, FA and FB are not even equal. FA and FB are not even equal. This is FA, this is FB. This is the point P, this is the point Q. Hey, once again, there would be a certain point on the graph of this function where the tangent becomes parallel to PQ, right? This is PQ. So, what is guaranteed is a point on the graph of the function. What is guaranteed is a certain point that corresponds to x equal to c belonging to a to b, such that the tangent becomes parallel to PQ. Yes or no? The physicality was this only. Physicality was this, right? That means the slope of the tangent at C, which is referred to as f dash C, is parallel to PQ. But that means has the same slope as PQ. F dash C is equal to slope of PQ, but slope of PQ is FB minus FA, y2 minus y1 by x2 minus x1. y2 minus y1 divided by x2 minus x1. That's the slope of the line. But then, this essentially to me, it's still Rolle's theorem. But then, the grand old Lagrange said, it's my theorem, his theorem, that is, he called it Lagrange's mean value theorem. Very mean of him, because it was actually Rolle's job. And all that he did was, he looked at Rolle with his head turned like 40 degrees. And he said, it's my theorem, LFBD. Hello, hello, hello. You know what I'm saying? This is Rolle's theorem, but the fellow, I mean, it's bad to comment on someone as great as Lagrange, who was like prolific in all regards. But this was perhaps one instance where, he just took life a little easy. He said, well, let me ride over Rolle for a while. Let me roll over Rolle. So he rolled over Rolle and he got his Lagrange's mean value theorem, right? Very mean of him. That's why, he chose this word, mean. I don't know if this was his own handiwork, but then, people later on call it mean value theorem. I'm sure they must have had this in mind. This to me seems like one sure short work of plagiarism. This was plagiarism. He must have been great, wherever you are, Lagrange. So that's Lagrange's mean value theorem. But then every time you apply Lagrange's mean value theorem or Rolle's theorem, you want to check for the continuity and differentiability of the function in the interval over which you want to apply Lagrange's or Rolle's theorem. Now, suppose I have two real numbers A and B. Let's say, only for definiteness, say A less than B. It does not matter though. Only for definiteness, let's say A is less than B. Then I claim that there must exist a C belonging to A to B. Then I claim that there must exist a C belonging to A to B such that 3C squared is A squared plus AB plus B squared. I claim that there must exist a C belonging to A to B such that 3C squared is A squared plus AB plus B squared. Now, in most cases, they would not offer the function fx to you on a platter. You would have to conceive the function based on the requirement of a certain situation. Now, 3C squared seems like the derivative of x cubed at x equal to c. 3C squared is like the derivative of x cubed at x equal to c, right? So then, you would be prompted to examine a function fx equal to x cubed. you will be prompted to examine a function fx equal to cube. And then you want to apply Lagrange's mean value theorem to this. You want to apply Lagrange's mean value theorem to this, which means existence of a C in the interval a to b, such that f dash C is fb minus fa by b minus a. fb minus fa by b minus a. But f dash C is like 3c squared. This is like b cubed minus a cubed by b minus a, which is a squared plus ab plus b squared. Right? Suppose I have a function y equal to fx. Have a function y equal to fx, and in the interval a to b, it's continuous and differentiable. It's continuous and differentiable. And if fb is 0, fb is 0. Then there must exist an x belonging to a to b. There must exist an x belonging to a to b such that fx plus f dash x is 0. There must exist an x belonging to a to b such that fx plus f dash x is 0. There is a function continuous and differentiable in the interval a to b such that fa is fb is 0. Then I claim that existence of an x belonging to a to b is guaranteed such that fx plus f dash x is, again in this case, you would have to imagine that this expression would come out of differentiating something. This expression would come out of differentiating something. If I look at phi x as e power x fx, look at phi x as e power x fx, then do you realize that you'll get e power x into fx plus e power x into f dash x. So e power x into fx plus f dash x would come, yes or no? Right? Now, fx is continuous and differentiable in the interval a to b, e power x is continuous and differentiable in the interval a to b. So this product is continuous and differentiable in the interval a to b. Moreover, phi a is going to be fa, which is 0, into e power a, and phi b is also 0. So phi x satisfies the condition of Rolle's theorem. Phi x satisfies the condition of Rolle's theorem, vanishes at the endpoints of the interval, and is continuous and differentiable in the interval a to b. So there must exist an x in the interval a to b for which phi dash x is 0. So existence of an x in the interval a to b, existence of an x in the interval a to b for which phi dash x is 0 is guaranteed. That's Rolle's theorem, right? Phi dash x means e power x into fx plus f dash x must be 0. Hey, but e power x is not 0 anywhere in the interval a to b. We are assuming a and b to be finite. We are assuming a and b to be finite. So e power x is not vanishing anywhere in the interval a to b. So this must vanish somewhere in the interval a to b at least once, right? So this gives me like fx plus f dash x becoming 0 at least 1x in the interval a to b. You know what I'm saying, right? I mean, no one would give you expressions that are difficult to imagine. You know, by and large, with a little inspection, you should be able to arrive at the function on which you want to deploy Rolle's theorem. In this case, the function phi x was not served to you. The function fx was given. From there, you had to construct a function phi x enjoying Rolle's criteria and whose differentiation gives you this or its factor or a multiple of this, fx plus f dash x. Clear? Again, Let's say there is a function fx continuous and differentiable in the interval a to b. Function fx continuous and differentiable in the interval a to b. And again, vanishing at the endpoints of the interval, fa is fb is 0. Then I claim there must exist a C belonging to A to B. Claim that there must exist a C belonging to A to B, for which fc plus cf dash c is 0. There must exist a C belonging to A to B such that fc plus cf dash c is 0. Again, you can't apply Rolle's theorem to fx and get this, right? Out of fx, you want to construct an auxiliary function whose difference, which will enjoy Rolle's criteria and whose differentiation would give you like fx plus xf dash x. What function which when differentiated would give you, yes, xfx. Xfx is the function which when differentiated would give you fx plus x f dash x. So you might want to examine and investigate phi x equal to x fx. X is continuous and differentiable, fx is continuous and differentiable, so phi x is continuous and differentiable. Check number 1. Check number 2, phi a is 0 because fa is 0, phi b is 0 because fb is 0. So then you can apply Rolle's theorem to phi x. There must exist a C belonging to A to B, for which phi dashed C is 0. Phi dashed x is fx plus xf dashed x, so phi dashed c is c fc plus cf dash c is 0. Let's go from the last problem now, maybe 27. f0 to 1 to 0 to 1 be a continuous function. Prove that fx is x for at least one x belonging to 0 to 1. Show that there must exist one x in the interval 0 to 1 for which fx is x, for which fx is. Now the domain of this function is 0 to 1. The codomain of this function is also 0 to 1. That means the function defined between 0 to 1 and all the y's of the function will lie between 0 and all the y's of the function will lie between 0 and 1. That means the entire graph of the function is contained in this square. The entire graph of the function is contained inside this square. At x equal to 0, the function assumes a certain value. Let's say this is the value at x equal to 0 of the function. At x equal to 1, it assumes a certain value that corresponds to q, the y of q, right? This is 0, 0 and this is 1, 1. This is 0, 0 and this is 1, 1. So this line is like y equal to x. This This is like y equal to x. This line is y equal to x. The graph of the function is continuous between 0 and 1, and it has to go from P to Q. If it has to go from P to Q, it has to seek the blessing of this dotted line at least once. In order to go from P to Q, it has to cross this line y equal to x at least once. It could have done it multiple number of times. Yes or no? Right? That means there is a certain x belonging to 0 to 1, and this is 45 degrees, for which, and this is fx, there is, for which fx is, there is at least one x in the interval 0 to 1, for which fx is clear. Clear? Twenty-sixes. Fx is continuous in the interval a to b, and fa is b, and fb is, we got to show that there exists at least one c belonging to a to b, for which fc becomes equal to c. fc becomes equal to c. Fa is a and fb is b, which means a comma b is a point on the graph of the function, right? Say x is a comma b would be a point like this on the graph of the function, and x is b and y is a, b comma a will be a point on the graph of the function. X is b and y is a. So there would be a point b comma a on the graph of the function. Right? These are points on the graph of the function for sure. Right? This is the line y equal to x. Do you realize that a comma b and b comma a are mirror images of each other about the line y equal to x? A comma b and b comma a are mirror images of each other about the line y equal to x. Means this is a point on the graph of the function, this is a point on the graph of the function. In order to go from P to Q, it has to at least pay tribute to the line y equal to x once. Right? And let's say that happens at x equal to c. That happens at x equal to c. So this is fc, then becomes equal to c on the line y equal to c. So this point is c comma fc lying on the line y equal to x. So c becomes equal to fc for one c belonging to a to, yes or no? The other way you can look at it is, construct a function phi x which is fx minus x. Construct a function phi x which is fx minus x. So phi a would be fa minus a, but fa is b. So this is b minus a, and phi b is going to be fb minus b, but fb is a, so this is a minus b. Okay, so phi changes sign in the interval from b minus a to a minus b. It changes sign in the interval. So phi must have a root in that interval. So phi must become 0 at least once in the interval. That means fx minus x must become 0 at least once in the interval a to b. That means fx must become equal to x for at least one x in the interval. Clear? Now let me get back to 21. It could have been done graphically, but to begin with, I'll just do it analytically. We want to talk of gx, which is f of x. Very simple really, because when I say f of x means replace x by fx wherever x appears. That's what it means, right? So we have like f of x is 1 plus fx for fx greater than or equal to 0, less than or equal to 2, and is 3 minus fx for fx greater than 2, less than or equal to 3. That's f of x, right? But then eventually the line of description must be entirely in terms of x, not in terms of fx. Now in any case, for this line, for example, fx could either be 1 plus x or could be 3 minus x. Even for this line, fx could either be 1 plus x or could be 3 minus x. So this line of description would lead to two further lines of description, one corresponding to fx equal to 1 plus x, one corresponding to fx equal to 3 minus x. Same with this line of description, fx could either be 1 plus x, one line of description, or the second line, fx is 3 minus x, the other line of description. So in general, it would expand to 4 lines of description, right? So f of x is 1 plus fx. So case 1 where I take fx as 1 plus x, fx as 1 plus x, when fx is 1 plus x, in any case 1 plus x must lie between 0 and 2. 1 plus x must lie between 0 and 2. Not only that, along with this, whenever you take fx as 1 plus x must also lie between 0 and 2. I'll repeat. X must also lie between 0 and 2. Because I've chosen fx as 1 plus x, so x must belong to this interval. Right? Second line. When fx is 3 minus x. When fx is 3 minus x. So let me choose fx as. So in the same line, take fx as 3 minus x. When I take fx as 3 minus x, one thing for sure, fx should still lie between 0 and 2. So 3 minus x and the moment fx is chosen as 3 minus x must be greater than 2, less than or equal to 3, intersection. Right? Now coming back to this, when 3 minus fx could be 1 plus x, fx could be 1 plus x, so 3 minus 1 plus x, where now 1 plus x must be greater than 2, less than or equal to 3. Intersection. And the moment you have chosen fx as 1 plus x must be greater than or equal to 0, less than or equal to 2. And then the final possibility, fx, this fx could be 3 minus x. This fx could be 3 minus x. So 3 minus x, where 3 minus x must lie between 2 and 3. 3 minus x must lie between 2 and 3. Intersection. The moment you choose fx as 3 minus x, x must lie between 2 and 3. X must lie between 2 and 3. Yes or no? So this is lines of description. Now all that you need to do here is find the range of x from here, find the range of x and take the common value of x. Same thing for this line of description, this line of description, this line of description. And it's possible that some of one or more of these intersections could also be a null set. You may not get, right? So can I leave it beyond this point for you to handle? You can find the intersection of these intervals, right? And you get simpler lines of description and whose continuity and differentiability could be examined with these. No? Within reach beyond this point, right? I'll leave it here. If you want to check for differentiability at x equal to 0, f dash 0 would be limit fx minus f0 by x minus 0, x tends to 0, right? And fx, when x tends to 0, that means when x is not 0, is given by x power m sin x, sin 1 by x. And f0 is 0. Obviously, for this limit to exist, m has to be greater than 1, so that this will tend to 0 and this will remain bounded. So this will tend to 0. So m has to be greater than 1 for this limit to exist. That means for it to be differentiable. Do you realize that? Because only if m is greater than 1. Now, see, this is bounded and this does not have a limit really, sin 1 by x. So for this whole thing to have a limit, this has to necessarily tend to 0. If it didn't tend to 0, then this limit will not exist. And this can tend to 0 only if m is greater than 1. Only if m is greater than 1. Okay. See, if m is less than 1, for example, what would happen to this? That means if m minus 1 is negative, if m minus 1 is negative, say, right? M less than 1 means m minus 1 is negative. That means m minus 1 could be written as minus p, right? So this becomes 1 by x power p, where p is a positive number, sin 1 by x. And then, as x tends to 0, this does not tend to a finite number, right? You know what I'm saying? So x minus m minus 1 has to be greater than 0, it can't be less than 0. So m has to be greater than 1 for this limit to exist. M less than 1, then it's not differentiable for sure. But if m is greater than 0, then limit fx x tends to 0 will be 0. Why? if m is any number between 0 and 1, for less than 1, m less than 1, we have seen that it's not going to be differentiable. But when m lies between 0 and 1, then limit fx, x tends to 0, will be limit x power m sine 1 by x tends to 0. If m is greater than 0, for sure this will tend to 0. And this limit will be 0 and the function would be continuous at x equal to 0. Right? But will not be differentiable because m is less than 1. And obviously then when m is less than 0, it's not going to be continuous and therefore not going to be differentiable at x equal to 0. F dash 2 is 4. Very simple. Limit f of 1 plus cos x. Hey, this is like limit ft minus f2. As x tends to 0, this tends to 2. This tends to 2. So t tends to 0. And we divide by t minus 2. So that this will become f dash 2. Then we multiply by t minus 2. T minus 2 means 1 plus cos x minus 2 divided by tan squared x. Yes or no? Where x tends to 0 and t tends to 0. T tends to 2. T tends to 2. I hope you realize what I did. This was t. So as x tends to 0, t would tend to 2. 1 plus cos x is t. Right? So t would tend to 2. So ft minus f2. And then I force from outside a t minus 2. So that this is going to become f dash 2. And then I multiply with a t minus 2 divided by tan squared x. Are you alright with this? This is f dash 2 which is already given. So 4 into limit. This is minus of 1 minus cos x by sine squared x cos squared x. X tends to 0. Right? This sine squared x is 1 plus cos x into 1 minus cos x. X tends to 0, etc. Are you okay with this? That is fractional part of x. That's gx. And f0 is f1. And hx is f of gx. That means f of fractional part of x. F of gx means f of fractional part of x. Now, let's say x equal to I is an integer. X equal to I is an integer. Let's say x equal to I is an integer. Then, as x tends to I from the greater than I side, fractional part of x tends to 0. As x tends to I from the less than I side, fractional part of x tends to 1. Yes or no? When it comes closer and closer and closer to 1 from the less than 1 side, less than an integer side, fractional part of x comes closer and closer to 1. From the greater than integer side, x comes closer and closer to 3. From the greater than 3 side, fractional part of x will come closer and closer to 0. Let's say 3.01, 3.001, 3.0001, it's coming closer and closer to 3 from the greater than 0 side, and fractional part of x is like 0.01, 0.001, 0.001, tending to 0, right? So then, limit hx, x tends to an integer from the less than an integer side. Less than an integer side means fractional part of x will tend to 1. Fractional part of x will tend to 1. So this will become like a f1, right? Limit hx, x tends to I from the greater than integer side. When x tends to I from the greater than I side, fractional part of x tends to 0. So this will be f0. But f0 is f1. So hx is continuous at x equal to I. Hx is continuous at x equal to I. Actually, the subintervals of description of this function is going to be x greater than or equal to 0, less than 1. This will become box sign 0. X greater than or equal to 1, less than 2. This will become box sign 1. X greater than or equal to 2, less than 3. Box sign 2. Box sign 3. X greater than or equal to 4, less than 5. Box sign 4. X greater than or equal to 5. 6 point, okay, 6 can be included. Box sign 5. And x greater than or equal to 6 but less than 2 pi. 2 pi is like 6 point something, right? It will be box sign 6. Sign 0 will be 0. Box sign 0 will be 0. Sign 1. 1 is less than pi by 2. I mean, all of these are in radians. So 1 is less than pi by 2. So first quadrant. So sign 1 will lie between 0 and 1. Box sign 1 will be 0. Sign 2. So 2 is second quadrant. Greater than 1.57. Greater than pi by 2. But less than 3.14. Less than pi. So again lying between 0 and 1. Box sign 2 would be 0. No? Box sign 3. 0. Because again less than 3.14. Less than pi. So this will lie between 0 and 1. 0. This minus 1. Third quadrant, right? Greater than pi, greater than 3.14, but less than 3 pi by 2. Less than 4.5 approximately. So then, again minus 1, because this will lie between minus 1 and 0, sign 4. Greater than 3 pi by 2, 3 pi by 2, 1.5, 4.5. So this is fourth quadrant. Fourth quadrant, so -1 again, because this will lie between -1 and 0. Now, hey, are you lost? You there with me, right? Sine 6, fourth quadrant, lying between -1 and 0, box will be -1. That's a description of this question. Kuch nahi, zeros, ones and -1s. Right? That's what you have.